From Mars to Moons, 10 key missions shaping humanity's quest for alien existence. The quest for extraterrestrial life has captivated human imagination for centuries, evolving from myth and speculation into a systematic scientific endeavor. As we advance technologically, our methods for searching for alien existence have become more sophisticated and targeted. This report explores 10 significant missions that are shaping humanity's exploration of life beyond Earth, particularly focusing on Mars and its moons as well as promising exoplanetary systems. 1. Mars exploration, the Martian frontier. Central to the search for life is Mars, a planet that has long fascinated scientists due to its historical potential for habitability. NASA's Perseverance rover, which landed on Mars in February 2021, is currently exploring Jezero Crater, believed to have once housed a lake. The rover's mission includes sampling Martian rocks and soil, which will be returned to Earth by the Mars Sample Return mission in the early 2030s for detailed analysis. The significance of these samples lies in their potential to reveal signs of past life, including microbial fossils if they exist. As planetary scientist Suzanne Schwinzer notes, if you have life, things look very different. Her hope reflects a broader optimism that we might uncover vital evidence of life's history on Mars. 2. The moons of Jupiter, Europa and Ganymede. Beyond Mars, the focus shifts to the icy moons of our solar system, particularly Europa and Ganymede. These moons are intriguing because they harbor vast subsurface oceans beneath their icy crusts. The Europa Clipper mission, set to launch in October 2024, will conduct detailed reconnaissance of Europa's ocean and its potential for habitability. Simultaneously, the European Space Agency's JWST mission, launched in April 2023, will study both Europa and Ganymede to gather data on their oceanic environments. These missions aim to assess the moon's potential to support life and lay the groundwork for future exploratory missions. 3. Saturn's Enceladus, a geyser of possibilities. Another moon of interest is Enceladus, known for its geysers that eject plumes of water vapor and ice into space. This phenomenon suggests the presence of a subsurface ocean, making Enceladus a prime candidate for the search for life. While current missions are focused on Europa and Ganymede, future missions may target Enceladus to analyze the composition of its plumes and search for biosignatures. The potential for discovering alien life in these icy worlds could redefine our understanding of life's diversity and origins. For exoplanet research, beyond our solar system. The search for life is not limited to our solar system. With over 5,500 exoplanets identified, astronomers are increasingly focused on studying these distant worlds for signs of habitability. The James Webb Space Telescope JWST plays a pivotal role in this effort, analyzing the atmospheres of rocky exoplanets, particularly in the TRAPPIST-1 system, where several planets exist in the habitable zone. Future missions like NASA's Habitable Worlds Observatory, expected to launch in the 2040s, will enhance our capacity to detect Earth-like conditions and potential biosignatures in exoplanet atmospheres. 5. The search for intelligent life, SETI and beyond. The quest for extraterrestrial intelligence, SETI, has taken new directions with initiatives like Breakthrough Listen, which aims to detect signals from advanced civilizations. Astronomer Jason Wright highlights the challenges of searching for signals, noting that while initial searches have yielded no clear results, advancements in radio astronomy, such as the upcoming Square Kilometre Array, are expected to enhance these efforts significantly. The continuous search underscores humanity's desire to understand if we are alone in the universe. 6. The role of technology, advancements in detection methods. Technological advancements have transformed our ability to explore and analyze distant worlds. For instance, JWST's capabilities allow astronomers to probe the atmospheres of exoplanets for chemical signatures indicative of life. Researchers are particularly interested in finding disequilibrium chemistry, where the presence of certain gases in unusual ratios suggests biological activity. These methods will be instrumental in shaping the future of astrobiology and our understanding of life's potential across the cosmos. 7. Anticipation and caution, the complexity of discovery. While optimism prevails regarding the potential for discovering signs of life, experts caution that such findings may not occur as swiftly as some hope. The timeline for significant discoveries varies among scientists, with some predicting evidence of organic compounds within a decade while others warn that the process may be gradual. As Lord Martin Rees, the UK Astronomer Royal, states, "I think we are really on the cusp of important discoveries." However, the nature of such discoveries will likely be complex, requiring careful analysis and interpretation. 8. The importance of Mars and its moons. Mars and its moons represent immediate targets for exploration due to their proximity and potential for habitability. The ongoing missions to these celestial bodies, including Perseverance and upcoming missions to Europa and Ganymede, reflect a focused effort to uncover evidence of past or present life. As scientists study these worlds, they hope to find definitive signatures of life or conditions conducive to its development. 9. The broader universe, implications of findings. The implications of discovering life, whether it be microbial on Mars or intelligent across the galaxy, would reshape our understanding of our place in the universe. Evidence of life would affirm that we are not alone, but it would also raise profound questions about the nature of life and its origins. Conversely, a lack of findings could indicate that life is exceedingly rare, prompting a re-evaluation of our assumptions about the universe. 10. Future prospects, a decade of discovery. The next decade promises to be a pivotal period in the search for alien life. Upcoming missions, including the Mars Sample Return Europa Clipper and advancements in exoplanet research, will provide critical data that may lead to groundbreaking discoveries. As we stand on the brink of this new era, the excitement and anticipation for what lies ahead are palpable. Conclusion. The ongoing missions to Mars, its moons, and beyond signify a comprehensive effort in the search for alien life. While there is hope for discoveries that could transform our understanding of life and the universe, the complexities of detection and analysis remind us that this quest is still in its early stages. The convergence of technological advancements, international collaboration, and scientific inquiry sets the stage for potentially momentous discoveries that could redefine our place in the cosmos. As we continue to explore the frontiers of space, the question remains: are we alone in the universe? The next decade may hold the answers. In the quest for extraterrestrial life, several counterintuitive insights emerge from recent explorations and missions concerning Mars, its moons, and exoplanets. Here are some key points that challenge conventional expectations. 1. Mars has a past habitability focus. While Mars has long been viewed as the most likely candidate for finding past or present life due to its historical wet conditions, the reality is more complex. The expectation that finding life on Mars would be straightforward is subverted by the understanding that even if signs of microbial life are discovered, they might not represent life that independently evolved there. Shared material between Earth and Mars early in their histories complicates the interpretation of any findings, suggesting that even positive results could point to life that originated on Earth rather than a unique Martian biosphere. 2. Icy moons as primary candidates. The icy moons of Jupiter and Saturn, particularly Europa and Enceladus, are now seen as potentially more promising for finding independent life forms. This runs counter to the initial focus on Mars. Instead of concentrating solely on the red planet, scientists are increasingly considering these moons due to their subsurface oceans, which may harbor completely separate life forms from those found on Earth, suggesting multiple origins of life in our solar system. 3. Technological limits in exoplanet research. The search for life on exoplanets, particularly those in the habitable zones around stars like TRAPPIST-1, reveals another layer of complexity. The James Webb Space Telescope JWST has advanced our capabilities to analyze exoplanet atmospheres, but the reality is that many Earth-like planets orbiting stars similar to our Sun are too dim to study effectively with current technology. The expectation of finding life in the near term is tempered by the limitations of our instruments. which prompts a more cautious approach to exoplanet exploration. 4. Gradual evidence of life. The assumption that the discovery of extraterrestrial life will be a definitive moment is misleading. Instead, evidence is likely to accumulate gradually, requiring careful interpretation and validation. Initial findings may not be conclusive and could lead to debates within the scientific community regarding their implications. This suggests that the path to understanding alien life may be more convoluted than a straightforward confirmation or discovery. 5. Null results as valuable data. The potential for searches to yield no evidence of extraterrestrial life raises the intriguing possibility that this outcome could itself provide significant insights. A negative result may indicate that life, if it exists, is exceedingly rare in the universe. This challenges the narrative that life is common and suggests a more nuanced understanding of life's distribution across the cosmos. 6. Intelligence and detection challenges. The quest to detect intelligent extraterrestrial life through initiatives like the Search for Extraterrestrial Intelligence SETI has yielded little success, highlighting the difficulty of discerning signals among the vastness of space. The expectation that we might encounter clear signals from intelligent civilizations is countered by the reality that any communication might be weak or indirect, requiring sophisticated methods to detect and interpret. 7. Expectations versus reality of discoveries. The anticipation of discovering complex multicellular life forms or advanced civilizations might overshadow the more likely scenario of finding microbial or chemically indicative signatures. The assumption that first contact would involve sophisticated communication or clear evidence of life is countered by the likelihood that initial findings will be subtle and require extensive analysis to understand their significance. 8. Interdisciplinary approaches. The exploration of extraterrestrial life increasingly involves interdisciplinary approaches integrating not only astronomy and planetary science but also biology, chemistry, and even anthropology. This broadens the scope of potential findings and interpretations, suggesting that our traditional views of life may need to evolve as we uncover new data. 9. Public perception and scientific communication. The potential for tentative findings to be misinterpreted or sensationalized in media poses a significant challenge for scientists. The expectation that the public will respond positively to confirmed discoveries is countered by the reality that nuanced scientific results often require careful explanation to avoid misunderstanding or misrepresentation. 10. The role of serendipity in discovery. Finally, the search for alien life is subject to serendipitous discoveries that can shift the focus of research unexpectedly. While missions are planned with specific goals, the actual findings may lead scientists in unforeseen directions, underscoring the unpredictable nature of scientific exploration. These counterintuitive insights illuminate the complexities and challenges inherent in humanity's quest for understanding alien existence, suggesting that the journey may be as enlightening as the discoveries themselves. The report, titled From Mars to Moons, 10 Key Missions Shaping Humanity's Quest for Alien Existence, provides a comprehensive overview of current and upcoming space missions aimed at discovering extraterrestrial life. While the summary covers significant advancements in missions, several important details may be overlooked by readers which are worth highlighting for their significance. 1. Mars Sample Return Missions Funding Challenges. The mention of the Mars Sample Return mission facing funding difficulties is a crucial detail that many might gloss over. The success of this mission hinges not only on the technological capabilities but also on the political and financial support it garners. If funding fails or is delayed, it could postpone the timeline for returning Martian samples, which are critical for understanding the planet's potential to have harbored life. The implications of this are profound. A delay could push back the entire timeline for understanding life's existence elsewhere in the universe. 2. Potential for discovering a second genesis of life. The distinction between finding life on Mars and discovering life on icy moons like Europa or Enceladus is significant. The report emphasizes that if life were found on these moons, it would suggest a different genesis of life from Earth, indicating that life could arise independently under similar conditions. This concept of a second genesis is pivotal as it would reshape our understanding of life's emergence and its potential ubiquity in the universe. Many readers might miss the broader implications of this, overlooking how it could fundamentally alter theories regarding life's origins. 3. Role of the James Webb Space Telescope JWST. While the report discusses the JWST's capabilities in examining exoplanet atmospheres, it is vital to note that JWST's design and mission were initially not focused on exoplanets. Its retasking for this purpose highlights an adaptive approach in scientific missions, showcasing how technology can pivot to meet emerging scientific questions. The capability of JWST to analyze atmospheric compositions could lead to groundbreaking discoveries of biosignatures, indicators of life, which could transform our understanding of habitability beyond our solar system. 4. Gradual nature of discovery. The report hints at the gradual process of confirming the existence of extraterrestrial life, suggesting that any findings will likely be tentative rather than definitive. This notion is significant because it sets realistic expectations for the scientific community and the public. It emphasizes the importance of caution in interpreting findings and the potential for miscommunication in media representations. The gradual accumulation of evidence rather than a singular moment of discovery reflects the complexities involved in astrobiology and may temper public reactions to initial reports of potential life. 5. The importance of atmospheric composition studies. The analysis of exoplanet atmospheres for disequilibrium chemistry as a sign of life is a critical area of focus that many may not fully appreciate. The ratios of gases like methane and carbon dioxide can imply biological processes if found in certain proportions. This method of detection could redefine our search for life, moving beyond direct observation of organisms to interpreting chemical signatures that suggest life's presence. This shift in methodology is significant as it opens new avenues for exploration and may lead to findings that are less direct but equally compelling. 6. The role of SETI and technological advancements. The ongoing search for intelligent life through initiatives like SETI and Breakthrough Listen is another area that may not receive adequate attention. The report mentions the limitations of current searches within 100 light-years of Earth but does not delve into how technological advancements such as the square-kilometer array could enhance our ability to detect signals from distant civilizations. This aspect underscores the need for continuous investment in technology to expand our search capabilities and the potential for unexpected discoveries. 7. Philosophical implications of a null result. The report touches on the possibility that many searches may yield null results, which is a significant philosophical point. A finding of no life could provide critical insights into the rarity of life in the universe. This could lead to a deeper understanding of our own existence and the conditions necessary for life to thrive. The implications of such a conclusion are profound as it challenges assumptions about life being common and could influence future research directions in astrobiology. 8. Interdisciplinary collaboration. The missions discussed often involve interdisciplinary collaboration among scientists from various fields: geology, biology, astronomy, and engineering. The complexity of these missions requires expertise from multiple domains, reflecting the collaborative nature of modern science. This aspect might be overlooked but is essential for the success of such ambitious projects as it fosters innovation and comprehensive approaches to solving the challenges of space exploration. 9. Cultural impact of discovering extraterrestrial life. While the report focuses heavily on scientific missions, the cultural ramifications of discovering extraterrestrial life are profound. The potential for finding life, whether microbial or intelligent, would not only revolutionize science but also transform philosophical, religious, and societal perspectives on humanity's place in the universe. This cultural dimension is significant and may influence how findings are communicated to the public and how society reacts to them. 10. The role of public engagement and education. Finally, the report emphasizes the importance of public engagement in the search for extraterrestrial life. As missions proceed and findings emerge, effectively communicating the science and its implications to the public is crucial. Misunderstandings or sensationalism in media coverage can lead to public mistrust or unrealistic expectations. Education and transparency will be vital in navigating the complex emotions and thoughts surrounding the possible discovery of life beyond Earth. In summary, while the report provides a detailed overview of significant missions related to the search for extraterrestrial life, it is essential to recognize the broader implications, challenges, and cultural dimensions of this quest. Understanding these nuances is crucial for appreciating the complexities of astrobiology and the potential impact of these discoveries on humanity's understanding of life in the universe. 1. Mars exploration and the Mars sample return mission. The Mars exploration efforts, particularly through NASA's Perseverance rover and the upcoming Mars sample return mission, are crucial in the search for past life on Mars. Jezero Crater's significance as a former lake bed highlights the potential for fossilized microbial life. The analysis of Martian samples could fundamentally alter our understanding of life's history on Mars, providing essential clues about the planet's habitability and the geological processes that occurred over billions of years. Suzanne Schwenzer's insights emphasize the importance of these samples in revealing the conditions that may have supported life, showcasing the intersection of geology and astrobiology. 2. Icy moons as habitable environments. The missions targeting the icy moons of Jupiter and Saturn, particularly Europa and Enceladus, signify a shift in the search for life beyond Mars. These moons are believed to harbor vast subsurface oceans, creating environments that could potentially support life. NASA's Europa Clipper and ESA's JWST missions aim to study these moons' oceanic conditions and assess their habitability. The scientific community's focus on these environments underscores the importance of exploring alternative habitats within our solar system where life could have evolved independently from Earth, thereby broadening the scope of astrobiological research. 3. Exoplanet research and the role of JWST. The search for life extends to over 5,500 identified exoplanets, with the James Webb Space Telescope JWST playing a pivotal role in analyzing atmospheres for biosignatures. The TRAPPIST-1 system, with its Earth-sized planets in the habitable zone, represents a promising target for future investigations. This research emphasizes the need for advanced telescopes to detect atmospheric compositions and chemical markers indicative of life. The potential discovery of biosignatures on exoplanets could revolutionize our understanding of life's distribution in the universe and the conditions that foster it. 4. Search for intelligent life and technological advancements. The ongoing quest for intelligent extraterrestrial life, exemplified by initiatives like Breakthrough Listen and advancements in radio astronomy, reflects humanity's desire to connect with other civilizations. The development of the Square Kilometre Array and other future telescopes will enhance our ability to detect signals from distant civilizations. This aspect of the search highlights the technological innovations that facilitate the exploration of the cosmos and the philosophical implications of finding intelligent life, potentially reshaping our understanding of humanity's place in the universe. 1. The Apollo 11 moon landing. 1969. The Apollo 11 mission marked a monumental achievement in human history, as it was the first manned mission to land on the moon. Astronauts Neil Armstrong and Buzz Aldrin spent approximately 21 hours on the lunar surface collecting samples and conducting experiments. This mission not only represented a significant leap in space exploration but also captivated the world's imagination about the potential for life beyond Earth. The findings from Apollo 11, including lunar rocks and soil, have contributed to ongoing discussions about the moon's geological history and its role in the broader context of planetary science. 2. The Viking program. 1976. NASA's Viking program consisted of two spacecraft, Viking 1 and Viking 2, which were sent to Mars to search for signs of life. Viking 1 was the first spacecraft to successfully land on Mars, conducting experiments to analyze the Martian soil and atmosphere. The mission included a series of biological experiments designed to detect microbial life. Although the results were inconclusive and sparked debates about the presence of life on Mars, the Viking program laid the groundwork for future Mars missions and intensified interest in the planet's potential habitability. 3. The Kepler Space Telescope 2009 to 2018, launched to discover Earth-like planets and other solar systems. The Kepler Space Telescope revolutionized our understanding of exoplanets. It confirmed the existence of thousands of exoplanets, many of which are located in the habitable zone of their stars where conditions might be suitable for life. The data collected by Kepler has fueled ongoing research into the characteristics of these distant worlds and has inspired missions aimed at analyzing their atmospheres for biosignatures, thus expanding the search for extraterrestrial life beyond our solar system. The future outlook for humanity's quest for extraterrestrial life is poised for significant advancements driven by ongoing and upcoming space missions, technological innovations, and a growing understanding of the universe. Here are key predictions for the future of this exploration. 1. Mars exploration and sample return. By the early 2030s, NASA's Mars Sample Return mission is expected to successfully retrieve samples collected by the Perseverance rover. Scientists anticipate these samples will provide crucial insights into Mars' past, potentially revealing biosignatures or evidence of ancient microbial life. The success of this mission could reshape our understanding of life's potential beyond Earth and offer a comparative analysis with terrestrial life forms. 2. Icy moons, Europa and Enceladus. The Europa Clipper mission, launching in October 2024, is set to explore Jupiter's icy moon Europa, while the JWST mission will focus on both Europa and Ganymede. By the early 2030s, data from these missions may uncover critical information about subsurface oceans, possibly harboring conditions suitable for life. Future missions such as the proposed Europa lander could aim to directly sample these environments, leading to definitive answers regarding extraterrestrial life in our own solar system. 3. Exoplanet studies with JWST and beyond. The James Webb Space Telescope JWST is already making strides in analyzing the atmospheres of exoplanets, particularly in the TRAPPIST-1 system. Initial results are expected to clarify whether these planets possess atmospheres conducive to life. By the end of this decade, findings could indicate the presence of biosignatures, potentially marking a turning point in exoplanet research. Furthermore, the anticipated Habitable Worlds Observatory set for the 2040s will enable more in-depth studies of Earth-like planets around Sun-like stars. 4. Breakthrough initiatives for intelligent life. The search for extraterrestrial intelligence SETI is evolving, with initiatives like Breakthrough Listen and the Square Kilometer Array, which will enhance our capability to detect signals from distant civilizations. As technology improves, the next decade may yield new insights, providing either evidence of intelligent life or reinforcing the notion that we are alone in the cosmos. 5. Broader understanding of life's parameters. The exploration of both Mars and the icy moons is expected to broaden our definition of habitability. Discoveries in extreme environments on Earth indicate that life may exist in forms previously unimagined. This perspective will guide future missions and research, allowing scientists to look for life in conditions deemed inhospitable, such as those found in extreme environments on other celestial bodies. 6. Gradual evidence of life. It is unlikely that the discovery of alien life will come as a singular definitive moment. Instead, evidence will accumulate gradually, with scientists ruling out alternative explanations. This methodical approach will lead to a nuanced understanding of what constitutes life beyond Earth, possibly fostering a paradigm shift in how we perceive our place in the universe. 7. Public engagement and scientific discourse. As discoveries unfold, public interest in extraterrestrial life will likely surge. Effective communication from the scientific community will be vital in managing expectations. Scientists will need to articulate the complexities of their findings, especially concerning ambiguous results that may suggest life but require further investigation. 8. Possibility of null results. There remains a distinct possibility that extensive searches may yield no evidence of life, which would still provide valuable information about the rarity of life in the universe. This outcome would stimulate philosophical and scientific discussions about life's emergence and its implications for humanity. 9. International collaboration and innovation. The future of extraterrestrial exploration will see increased collaboration among nations and private entities. Innovations in space travel, robotics, and life detection technologies will make missions more efficient and effective, enhancing our collective ability to explore and understand distant worlds. 10. The role of artificial intelligence. AI technology will play a significant role in analyzing vast amounts of data from space missions. Machine learning algorithms could identify potential biosignatures in atmospheric compositions of exoplanets or analyze geological data from Mars and icy moons, accelerating the pace of discovery. Conclusion. The next decade is poised to be transformative for humanity's quest for alien existence. With groundbreaking missions to Mars, its moons, and beyond, coupled with advanced astronomical tools, we are on the cusp of potentially revolutionary discoveries. Whether we find evidence of life or not, the journey itself promises to deepen our understanding of the universe and our place within it, fostering a sense of connection to the cosmos that transcends our earthly existence.